Hello everyone and welcome. I'm Max and today I'll be talking about particle emissions from fused filament fabrication 3D printer. Let's dive into the subject by looking at a small literature review. The first article that was ever published regarding particle emissions and 3D printers was by Stevens et al. In 2013. Their experiment was quite straightforward. They used a CPC and SMPS, so a particle counter and a particle size distribution analyzer, and placed it in a room where two 3D printers printed with PLA, and during the second stage they added 3 additional 3D printers that printed with ABS. They estimated that PLA must emit about 20 billion particles a minute and ABS about 200 billion particles a minute, but they also clearly stated in their article that further research was needed. Kim et al. In 2015 followed. Their experiment involved a 1 cubic meter size acrylic chamber where they placed a 3D printer inside, and they investigated 2 different PLA brands as well as 1 ABS brand. They showed that PLA emits about 500 million particles a minute regardless of the brand, and ABS emits 16 billion particles a minute. Kazim et al. In 2015 followed and investigated not only PLA and ABS but also other polymers, but showed that Kim et al. Was right with their estimates that PLA emits about 100 million particles a minute and ABS about 20 to 90 billion particles a minute. So the very first study had slightly higher numbers than the polymer actually emits. Interestingly, Azimi et al. In 2015 also investigated other polymers like PC, PET, nylon, and HIPS, and showed that these polymers emit in a range between PLA and ABS. So PLA will always be your lowest particle emitter and ABS will always be your highest particle emitter. Kim et al. And Azimi in both studies also investigated VOC, so volatile organic compounds, so the gases that are being emitted during the printing process. However, I'm not going to go into this area because or subject area, because otherwise this video would become too long and too extensive. And personally, I only studied particle emissions. Particle size was also investigated by Stevens et al. In 2013. They showed or measured that PLA emits in a particle size range between 48 and 65 nanometers, or at least that's where most of the particles are emitted from in that particle size range, and ABS emits in a particle size range between 15 and 49. Kim et al. In 2015 also investigated particle size. The number in the bracket is the geometric mean, particle size mean of the before they started printing, so it was 45 nanometers before they started printing, and during the printing process the particle size geometric mean was 28. This means the Kim et al. Had lower particle sizes being emitted by a PLA than Stevens and al. Had in 2013. For ABS, Kim et al. 2015 had 33 nanometers as a geometric mean, meaning this would actually fit quite well into the particle size range from Stevens et al. 2013. However, a newer study now from 2017, Mendes et al., a link to that study is in the description and it's freely available, so you can read through it for free and, well, go for it because it's free. And they showed an interesting measurement because they measured the particle size for ABS in a geometric mean size of 6 nanometers, and if they increased the temperature it went up by 9 nanometers. And this is an actually quite interesting find, and I will get into that later on in the presentation again. Also, Mendes et al. In 2017 measured a high particle size, high particle numbers in a particle size range between 1 nanometer and 3 nanometer. However, this is quite complicated to measure and you need specialized equipment for that. We're talking about very, 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 very small particles here. So 1 nanometer to 3 nanometers, an oxygen atom has about 0.1 nanometer is 1.1 nanometer in size. So we're talking about very, very, very small particles here. So what is the problem with ultrafine particles? Well, by definition, they're smaller than 100 nanometers in size. So that's why they're called also nanoparticles. and they act or behave like air nanoparticles. And that's an issue because our filtration system, natural filtration system, our nose hair, do not work anymore with these particle sizes. So for bigger particles, like if you work in a dusty environment like a woodworking shop and you blow your nose at the end of the day, you can see all the particles that your nose hair filtered out in your snot, basically. So, but with these ultrafine particles, these filtration systems do not work anymore, and they can get into our lungs. And because nanoparticles have a high surface to volume ratio, they can be very chemically active. So, me personally, I investigated particle size at the end of 2015, just before Kim et al. Published their papers, and thought about particle emissions and what kind of factors could influence particles emission. So during the printing process, we print with different speeds. We might print with the cooling fan on. We might increase the temperature of the hot end to get better layer adhesions, and so on and so forth. So we change a lot of factors, and I think all of these factors can influence particle emission. So I went up to my professor and asked him if I could investigate these, and he told me to invest one specific variable first, and we decided to look at temperature. And we decided to not create a experiment chamber which could fit a whole 3D printer, but rather thought, okay, well, the emissions actually come from the hot polymer and not the construction of a 3D model. And as such, we just created a small chamber around the hot end. It's a metal box, 10 by 10 by 20 centimeters, so in total 2000 cubic centimeters. Inside there is a E3D V6 hot end, and on top of there is the feed mechanism, so the extruder that feeds then the polymer filament into the hot end. We have a compressed air inlet, so the volumetric flow rate of the air was regulated by a rotometer and was set to 3000 cubic centimeters per minute. The air inlet was aimed at the E3D V6 fan, so the cooling fan that cools the cooling fins. So we had a decent air circulation inside the experiment chamber. And we had at the exhaust air outlet a connected ACBC, so a condensation particle counter, so a particle counter. The particle counter could measure particle sizes down to 4 nanometers, and the model, it was a TSI model 3775. At the exhaust air outlet, we have a valve. This valve was needed to create a very slight overpressure inside the experiment chamber, which was around 2 millibars, and that was verified by this manometer right here. Why did we need a overpressure? Because the outside air should not influence the particle concentration inside the experiment chamber, so we created this small overpressure so that any leak would rather leak out than the air would leak in, because the outside air had more particles than our compressed air. Our compressed air has less than 1 particle per cubic centimeters, which is very, very clean air. As a reference value, our air that we breathe on a daily basis has about 5,000 to 10,000 particles per cubic centimeters. So if we had a leak and it would leak in, it would definitely influence our particle emission measurements. So here is a picture of the experimental setup. You can see here the PLA, the filament I was using was PLA, so I only investigated PLA. I only used natural PLA because I wanted to exclude color pigments as a potential emission source. I tested this as well, and as it turns out, the emission rates do increase slightly but are negligible if you have a colored filament. So these are not, the color pigments are not your main emission source. You can see here the metal box. On top of here is the feed mechanism or extruder. It's a Greg Wade extruder. There the exhaust air outlet with the valve right here, the connection to the manometer, the compressed air inlet, and this is the cooling air inlet, which you can see here. And I'm gonna go later into this why I needed a cooling air inlet. The experiment procedure is quite straightforward. First, I measured the background measurement, which was basically 0 particles per cubic centimeters. Then I started to G-code, which showed the hot end to heat up to a certain target temperature, which was usually reached in 2 minutes. And then the extrusion of the polymer started for 25 minutes, and then a 1 minute decay period. I investigated 2 nozzle sizes, an 0.4mm nozzle and a 0.8mm nozzle. I assumed that the 0.4mm nozzle printed at an 0.2mm layer height, and the printing speeds I investigated were 30, 60 and 90mm per second, and here are the corresponding volumetric flow rates. The 0.8mm nozzle I assume printed at an 0.4mm layer height, and again 3 printing speeds were investigated, 20, 30 and 40mm per second. And why are these printing speeds lower than the 0.4? Or, well, you can see that the volumetric flow rates already at these printing speeds is quite high. The 40mm per second is actually exceeds the capabilities of the E3D V6 hot end. So this printing speed is more of an experimental investigation rather than actual printing speed that could be used for printing a 3D object. How did an experimental run look like? So once it started extruding, we can see a very steep increase in the particle concentration that lasted until the 2nd minute, and then after the 2nd minute we have a decrease of the particle concentration down towards a steady state. Why do we have such a peak width and such a peak, like the peak width and this peak height? Well, I thought a lot about this, and I figured that, well, if the hot end starts heating up, the heater cartridge on the left side starts overheating this left side until the thermistor here on the right side can actually measure the temperature increase. So you will have a temperature gradient kind of at the beginning of your extrusion process itself. So while the hot end, while the filament is still sitting inside here the heater block and it's being heated while the heat block heats up, you have a overheated filament in there, and that's why you have this steep increase of particle emission at the beginning, because you have such a overheated polymer being extruded. So this was already a first indicator that the temperature does have an influence on the particle emissions. Also, one interesting factor is the heat distribution can maintain itself for longer than 20 minutes, meaning after the experiment was finished, the extrusion process itself was finished and the hot end started cooling down, and after 20 minutes it told me, the thermistor told me, oh well, we have cooled down to ambient air temperature, and I wanted to repeat the process itself. The peak itself was not repeatable anymore, so the peak was a lot smaller, and then we reach a steady state a lot faster. So I couldn't repeat the experiments as fast and had to wait then 1.5 hours before I could actually get repeatable results. And that's why I have here at the beginning of this slide this cooling air inlet. So this cooling air inlet blew compressed air over the heater block and as such cooled it down. So I let it cool down through natural convection for 10 minutes, and then opened up the valve here and let the cooling air blow over the heater block and let it cool down for 20 minutes, and then I could get repeatable results. So each experimental run which actually would last 1 hour. So as you can see here, half an hour for the experiment itself, and then half an hour of cooling down. The main variable, as I already mentioned, is what I was changing was the temperature, and I also investigated then what is the actual nozzle temperature. So I used a thermocouple which was 3 millimeters in diameter and put it down into the shaft of the E3D V6 hot end until it reached the nozzle, and measured then the nozzle temperature as such. I started with 180 degrees and measured then an actual nozzle temperature which was around 156, and then started to increase the temperature, the target temperature, by 10 degrees, but actually got only an increase in nozzle temperature of around 7 degrees. So this means that after a while, when you reach the 300 degrees Celsius, or as a target temperature, you actually just got a nozzle temperature of 245. In the following graphs, which will then follow, I use the measured nozzle temperature because I think this is the more appropriate value than the actual target temperature. Since different hot ends are built differently, this means that if you set a certain target temperature in your firmware, it doesn't mean that your nozzle actually has that temperature. So if someone wanted to repeat my experiments with a different hot end, they should then measure the actual nozzle temperature and then can maybe get comparable results to mine. I investigated two emission dimensions. First of all, the excess emissions and the steady state. So the steady state is reached usually between the 10th and 15 minutes, depending on the run, and is when the particle emission basically is stabilized. The excess emissions are all the particles that are being emitted because you don't have a homogeneous heat distribution inside the heater block, and as such extrude hotter filament at the beginning of your extrusion process. So these are all the particles which are, in air quotes, are necessarily created because you have an inhomogeneous heat distribution inside the heater block. Okay, let's get to the results. First of all, steady state, 0.4 millimeter nozzle. We have here on the y-axis the average steady state logarithmically plotted over the measured nozzle temperature. The measured nozzle temperatures correspond to the target temperatures of 220 degrees Celsius, 230 degrees Celsius, 240 and 250 degrees Celsius. These are the printing speeds. So the slow one was, just to remember, is the 30 millimeters per second, 60 millimeters per second, and 90 millimeters per second. We can see here that the average printing speed of 60 millimeters per second is our highest particle emitter, while the fastest printing speed is our lowest particle emitter. And these are not linear functions, these are exponential functions, since the y-axis is logarithmically plotted. And as you might have already seen, the particle emissions per minute do not even closely resemble those that were mentioned in the articles before. To clarify, I worked very cleanly. And this means that before I even started my experimental runs, I put the disassembled the assembled parts from the E3D hot end. I put in ethanol, put it in an ultrasonic bath, then assembled them, put them into the experiment chamber, heated up the hot end to 285 degrees Celsius, left it there for 8 hours until literally no particles were emitted anymore from the hot end itself, and then started the experiments. Once the extruded polymer accidentally maybe found its way onto the nozzle, that happened usually at the beginning of the extrusion process, when one side of the extruded filaments cools faster than the other, so it starts slightly curling, and this curling, if that was too extreme, could touch then the nozzle, and then you would get very high amount of particles emission, and then I would disassemble it and clean it again. This didn't happen too often, just I think once or twice. And but I worked very cleanly, so I just wanted to see what the particle emissions were from the extrusion process itself. You're gonna say now, well, my hot end will never be this clean, and I agree. However, I tried to do a experimental run also where there was a contaminated nozzle and heater block, where there was some residual filament on there, but the problem was I couldn't get repeatable results. You get very high emissions from these contaminated heater blocks, let's say it this way, but they are not consistent. So if you run it first time, you get maybe a few 100 million particles a minute, and then the second run you would only get, let's say, 50 million particles a minute, and then the third run would be only 10 million particles a minute. So the burning off of the filament over time will emit less and less particles. So afterwards you just would have, you would be left over with black carbon, which would not emit any more or very little particles anymore. So you couldn't get repeatable results, and I think this would then not actually depict an accurate picture just because you have a contaminated nozzle. My assumptions were that in the future, if we can create hot ends in such a way where the heater blocks will not be contaminated again, these emission sources are actually going to be our reference value. And they show that if you actually print close to the melt temperature of, in this case, well, PLA, you emit very little particles. But once you increase your temperature just slightly by target temperature by 10 degrees, actual nozzle temperature by 7 degrees, you can see there's a difference between 1,000 particles a minute to up to 17,000 particles a minute. And then if you increase further the temperature, it's an increase from 17,000 close to 1 million. And then once you're at 1 million, you can already reach 17 million. So a few degrees Celsius make a difference between a few thousand particles and millions of particles. So this is actually the interesting finding in my bachelor thesis. And also that these functions, exponential functions, actually depict the measured points here quite well. So each run, by the way, each dot here was run 3 times and then an average was taken. For the 0.8 millimeter nozzle, you can see the slowest printing speed is our highest particle emitter, while the fastest printing speed is the lowest particle emitter. But as I already mentioned, due to the high volumetric flow rate that exceeded the V6 capabilities, we don't get a good fit of the exponential function. And what is interesting to note here is that basically the slow printing speed, or the average printing speed, is just shifted slightly to the right. So you can see here that these emission rates are basically on the same level, which I find interesting. This might mean that for instance, so this is the target temperature was 220, 230, 240, 250, meaning if you have here a target temperature of 220 degrees Celsius and you need to set the temperature slightly higher for the average printing speed because you don't get otherwise a consistent flow out of it, the polymer, the extruded polymer, might have the same temperature that's being extruded. So by the way, this is also why there is a 4th point here missing of the fast, because I needed to slightly overheat the hot end to actually get the extrusion process itself going. The exponential functions I think are quite interesting to look at, especially the parameter b here. The parameter b is around 0.45, you can see 0.42, 0.43 and so on. So the logarithmic slope is basically the same for the regardless of the nozzle size, except the fast is kind of an outlier, as already mentioned. First of all, the fit is not that great, and also the logarithmic slope is not that high. This has to do again because the V6 is exceeding its capabilities with this with an 0.8 millimeter nozzle printing at 40 millimeters a second. The parameter A, as you can see here, basically goes towards 0. So at 0 temperature, you emit 0 particles, you could say, which seems obvious. And you can see that the coefficient of determination is quite well for most of the, except for the fast one, but for most of the printing speeds and nozzle sizes. As I already mentioned before, excess emissions, I'm just quickly going to go over these, are the particles that you emit because of the heater block not having an homogeneous heat distribution at the beginning of the extrusion process. We can again explain those increases in particle emissions with an exponential function. Again, the y-axis is logarithmically plotted over the measured nozzle temperatures. This is the 0.4 millimeter nozzle, and as you can see, well, we can explain with an exponential function this increase, but the fit is, well, okay-ish, I would only say. It actually got worse for the 0.8 millimeter nozzle. We had quite extreme excess emissions at the beginning. It was a lot worse for the 0.8 millimeter nozzle than it was for the 0.4, so there's literally in particle emission bursts at the beginning. Again, this has to do with overheating the filament and the heater block having an inhomogeneous heat distribution at the beginning. We can again see that we can exponentially explain the increases, but the fits are, well, as you can see here, okay-ish, but well. Again, the logarithmic slope, quite interesting, 0.38, 0.38, 0.32, 0.35. So the slope is quite similar. Again, fast is an outlier, and A tries to go towards 0. The exponential growth is actually with, you can't visualize it that good, I think, in the graphics before, so that's why I did a 3-dimensional diagram right here, so you can see a bit better how extreme these are. So for the 60 millimeters per second, our highest particle emitter for the 0.4 millimeter nozzle at a steady state, you can see that you have a very sharp increase, while the 30 millimeters and the 90 millimeters are, well, not that higher particle emitters. And the same goes for the 0.8 millimeter nozzle. You can see that the slowest printing speed has this extreme curve up. As you increase the temperature, the particle emissions increase quite drastically, from a few million up to 17 million around, and then that the 30 and the 40 are actually low particle emitters, or are acting so extreme with temperature. And now you're gonna ask yourself, why is that so? Why is, with an 0.8 millimeter nozzle, the slowest printing speed the highest particle emitter? Why for the 0.4 millimeter nozzle the highest, the average printing speed is the highest particle emitter? And at the beginning of my bachelor thesis, my assumption was the slower you print, the more likely it is that your polymer reaches the actual temperature of the nozzle, and as such the slowest printing speed will emit the highest number of particles. This would be true for the 0.8 millimeter nozzle, but it was not true for the 0.4 millimeter nozzle. So a new hypothesis had to be thought of, and my professor thought of, okay, well, think of this created surface area. So if we extrude, you create a certain surface area. So the extruded polymer has a certain surface area that you create per time, so squared millimeters per second. And you can see here for the 0.4 millimeter nozzle that at the printing speed of 30 millimeters per second, you create about 24 squared millimeters per second. And then this increases then obviously with the printing speed. And this is the dwell time, so the time the filament stays inside the heater block before it's being extruded. And then the assumption was, okay, so 42 seconds is quite a long time. That will definitely make sure that the filament reaches the temperature, but it could be that 20 seconds would suffice to reach the nozzle temperature. So you have a higher surface area per time created, and also you reach the temperature of the hot end, thus you create a longer string of filament that can maintain its heat to emit particles. And while the slower printing speed has creates less surface area per time, and as such only a shorter length of filament can still emit particles. However, then at a certain point with 90 millimeters per second, you undershoot a dwell time, which then cannot make sure that it reaches the temperature. You create a high surface area per time, but you have a colder filament that's being extruded, and as such it emits less. And the same goes for the 0.8, so the 16 seconds would suffice still, and you create a decent amount of surface area per time, and thus you emit a high number of particles. But as you then increase your printing speed, you have less time, and less the likelihood that your filament actually reaches the temperature will decrease, and as such the added surface area per time does not give you more particles. This could be analyzed, or could be justified or verified by an infrared camera. So what we have here is a heating element, which I could set a target temperature of 130 degrees. And I blocked out the heater block here on top, so we can see just the filament coming out of the nozzle right here. And as such, we can see the temperature gradient of the extruded filament. I had to block out the heater block because it was so hot that I couldn't see anymore the temperature gradient of the extruded filament. So that's why I had to block it out and set a heating element right here, and fit the heating element's temperature to the extruded filament. We can see here the 0.4 millimeter nozzle printing at 30, 60 and 90 millimeters per second, and here the 0.8 millimeter nozzle printing at 20, 30 and 40. The surface area temperature hypothesis kind of fits for A here for 30 millimeters per second. You can see here a short section only maintaining the heat for a short time, and as such a small area that might emit particles. And we can see already here that after a while it already reached ambient air temperature, the extruded filament. We can see here for 60 millimeters per second that it can maintain longer a heat or a greater surface area or greater length of filament that can emit particles, but this also goes for the 90 millimeters per second. However, as you can see here, it seems that both of them reach after the same amount of time, same amount of length, the same temperature, and you create here a much bigger surface area per time than you do for the 60 millimeters per second. So this means the 90 millimeters per second must cool down faster than the 60 millimeters per second. But still, you would say just from the images, these two would emit the same amount of particles because the same amount of length of filament stays hot the same amount of time. So the surface area temperature hypothesis only fits, well, okayishly. We can also see for the 0.8 millimeter nozzle right here, you would assume that the fastest printing speed emit the most particles per time because more length of filament stays hot longer than the 20 millimeters per second right here, the slowest printing speed, which should be our highest particle emitter. So the surface area temperature hypothesis fits okayishly, well, kind of good to the actual infrared camera images. So by this time already I was quite desperate because I thought, okay, I'm doing some mistakes here. How can other papers and articles measure these numbers of particles and I can't even reach those particles even if I go up with the temperature over the actual printing temperatures. So I got quite frustrated and thought, okay, what else could influence the particles emissions? And I got back to the thing, okay, maybe 3D printing a model does influence particles emission. Why so? Because back then I called it the ironing effect. As you extrude the filament, extrude the filament, your nozzle sweeps over the extruded layers, and as such there's a contact between the brass and the polymer. And as I already mentioned, if the polymer finds its way onto the hot end or the nozzle and starts baking itself or burning up, it starts emitting a high amount of particles. And I thought even just maybe a short contact between the brass nozzle and the extruded polymer could emit additional particles. So I decided, okay, let's put the whole 3D printer inside an experiment chamber and measure those particles, and I should measure the same amount of particles. So that's what we did. We used an oil drum which has 2008 cubic centimeters is in size. Again, the compressed air rotometer, this time 10 times more air per time, so 30,000 cubic centimeters per minute. Remember, we have 100 times more volume now, experimental volume. So before that, the small extruder setup had 2,000 cubic centimeters volume. This has now 208,000. So we have a 10-fold increase in compressed air, but a 100-fold increase in volume. So the air exchange is less in this case. Again, CPC, manometer to check that no outside air comes in, and so on and so forth. This is a metal pipe. The metal pipe then guided the compressed air down to the bottom, and then we sucked out the air here on top. This is the results of our experiment. So this is 220 degrees, this would be 230, 240, 250, and 260. You can see here I jumped the whole 20 degrees target temperature. That was because I got kind of frustrated when I saw the first results and still did not get these emissions. Until I put in 260 degrees Celsius and I reached the 100 million. Yay me! So this is the box, by the way. So this is the that you can compare what I measured for the same printing speed in the box. By the way, I printed a cylinder in vase mode, meaning that with 60 millimeters per second. So you have a consistent flow of polymer. Because if you would print a box, acceleration and jerk would then mean that you would slow down and increase again the printing speeds constantly. So I needed a consistent movement of the extruder head, and well, you can do that only with a cylinder. So this is once you print a cylinder, and could be as such also comparable to the box experiment. We can see here that the logarithmic slope is not as high in the barrel as it was for the box. It could have multiple reasons and so on and so forth. I'm not quite sure why we have such a low emission rate even in the barrel, because my extruder or my hot end was not clean, as it was clean inside the box. So it was my standard hot end that had some contaminated and burnt off filament on there, but I did not have a failed print in quite a while, so maybe already this residual polymer on the heater block kind of burnt off, and the hot end itself did not emit a high amount of particles. I could never quite explain why I measured so few particles and the other publications did. The CPC, I changed also the CPC at one point, same model obviously, but we have multiple in the institute, but I changed the CPC just to see maybe if mine was faulty. It didn't. The other CPC gave me exactly the same numbers, so it could not have been the CPC. The particle size it could measure went down to 4 nanometers, so it's not like I excluded a certain small particle size. So the next thing I thought of, and this is a wild hypothesis. It's truly a wild hypothesis, but I love making wild hypotheses. It's part of the fun of doing science. So if someone heard about crystallization, it's a phenomenon. If you, for instance, try to dissolve some crystals, for instance sugar, inside water, that goes into a certain concentration for a certain water temperature. After a certain amount of sugar, you just cannot dissolve it anymore. In some cases, if you have a very, very clean or distilled water, you can even go further up than this curve right here. So you have a super saturation. And then once you just throw in a small dust particle, you can see literally crystals quickly forming and falling down, just like in a snow globe. So this would be called a crystallization nucleus. So that's the thing I thought maybe was also a reason why I didn't measure that many particles, because maybe a lot of gases, because I could smell each time I opened the box or the barrel, I could smell literally gas, like the gases that were emitted. You have this sweet smell that comes from PLA. Everybody who prints a lot knows that smell from PLA. It's very distinct. And I thought, okay, well, maybe due to this particle-free air that I push into the barrel and to the box, and there is no kind of crystallization nucleus, so the gases cannot agglomerate in such a way, and cannot form very small particles. So maybe the particles that were emitted were in a particle size range between 1 nanometer and 3 nanometer, as the previous study from Menes et al. Showed, and as such the CPC could not measure them. And only once there was a high enough number of very small particles being emitted, they could start agglomerate and make bigger particles that could then be measured by the CPC. However, this is a wild hypothesis. You could prove that by creating an experiment. I wouldn't do the barrel experiment because you have a lower air exchange rate and so on and so forth. It's bigger and so on. I would rather actually go back to the box experiment and put right in front of there a box or a small crystallization with a salt creator. I'm not quite sure how it's called in English. I'm sorry for that. And specifically, it creates very small particles, or you can create small particles that you can then add to your compressed air, to your clean compressed air, and as such then see what comes out at the end. So maybe particle concentration does have an influence on how particles are created with the extrusion of a polymer. Also, what could be interesting is to put a box just before there, so you can have maybe a dwell time, so that you leave the gas basically stew itself inside the box, and maybe it creates then more particles, and then let it suck out, and then you could just put bigger and smaller boxes in there, so the dwell time is different for the gas, and maybe you could see a particle concentration increase. So these would be kind of new setups I would think of if I had a chance to again investigate particles emissions. However, what do people now say can I take away? There's all this sciencey stuff. What can I take away from this? Well, it's difficult to say. First of all, I don't think there is a sure way to make a particle-free printer. I think personally what helps the most would most likely be a charcoal filter. A HEPA filter, I'm not quite sure if it can get out all those nanoparticles out of the air. It would be interesting though to find out how those particles are being created, and then to what size they come into what state, because then we might build a 3D printer that could be particle free in the future. But that's a long way. So what can you do now? Well, don't print in your bedroom. Maybe try to get a room that is dedicated to your 3D printer with a window, and if you don't have a window, then at least try to get a charcoal filter so gases are being filtered out of your air. That might be the best approach you could currently do to avoid particle emissions. I hope you learned something during this presentation and got a clearer picture how particles are being created by 3D printers, or how they could be created by 3D printers, and what factors influence them. Especially temperature is a big factor that influences particle emissions. My next video will be maybe about air filtration, ultrafine particles, or it will be about the 3D printing survey, the future of 3D printing, which I did just quite recently. Thanks for watching. I hope I see you next time in my next video. Until then, bye.